Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll derive an equation for boundary layer thickness, shear stress and coefficient of drag, and these are the expressions will be derived from a velocity profile of laminar boundary layer. So the velocity profile of laminar boundary layer will be given, and we need to derive the expression for these are the three terms what is given, that is boundary layer thickness, you can see boundary layer thickness and shear stress and the coefficient of drag. And in terms of Reynolds number, we need to identify this equation in terms of Reynolds number need to be formed. So the question is given here for the velocity profile of laminar boundary layer flows given as U by capital U equal to 3 by 2 into y by delta minus 1 by 2 y by delta whole cube. Find an expression for this boundary layer thickness, shear stress, coefficient of drag in terms of Reynolds number. So this kind of questions may be given in terms of problem, or it may be given in kind of derivation type. Like some questions will be given just derive these equations like that. So in the previous lecture also we have derived a similar kind of an expression, but there the velocity profile was different, and here the velocity profile is different. So though the velocity profile is different, our equations or the answers will come differently for the delta, tau naught and CD. So first of all, let me write down, let me write here the solution suppose, and here first of all I'll write this velocity profile that is given small u by capital U, and this is 3 by 2 and this is y by delta, and this is minus 1 by 2 and whole bracket y by delta q. Okay, and this is the velocity profile. Okay, and now this value we need to put in the von Karman momentum integral equation, which was derived in our previous lectures. And that if you see that video, we can get the equation. There we got the equation for von Karman momentum integral equation, that is tau naught by rho u square, tau naught by rho u square equal to, and this is del by del x bracket start integration 0 to delta, and this is actually the equation is small u by capital U, and again bracket start 1 minus small u by capital U bracket close, and this is dy, and here the bracket will be again close. Okay, so this was the equation actually we have derived in the von Karman momentum integral equation. Okay, so now we need to just put this value of u by u in the momentum integral equation. Okay, and now the velocity profile what is given small u by capital U, this value we need to implement in this equation. So after substituting this value in this equation, again the equation will be written in form of like tau naught by rho u square equal to del by del x bracket start integration 0 to delta. Again you can see this is the whole term we need to write here. That means again we'll give a again square bracket here. So this is 3 by 2 and this is y by delta minus 1 by 2, this is y by delta whole cube. Okay, and this is bracket close. Again this multiply of this one, so that again we need to write this is like 1 minus, again one more term will come, that one will give in this curly bracket, and this is 3 by 2 y by delta, and this is minus 1 by 2, and again here y by delta whole cube. Okay, and this is bracket complete dy, again one more square bracket complete. So this is the whole term what we have written in form of just we have kept the value of u by u on the von Karman equation. Now if you just elaborate this equation, what we will get here, this is del by del x, and this is bracket start integration 0 to delta, and this one we can write this is 3y by 2 delta, and this is y cube minus 2 delta cube. Okay, this is one equation, and apart from that what will get another one equation, that is 1 minus 3y by 3 delta plus this one is there 1 by 2 minus something is there, so that will be minus of this minus, so that is plus, so plus this is y cube by 2 delta cube. Okay, and this is bracket close, whole bracket, this is dy. Okay, now again we can write this equation in terms of like, just you elaborate this equation, or you can do one thing, you just multiply this one term to other term, one term to other term, like that. So that is, this one we can do 0 to in delta 3y 2y delta into 1. So we'll give another bracket here, so that I'll write 3y by 2 delta, then minus 3y by 2 delta minus 3y by 3 delta here. Okay, so here we'll get what, 9, this is 3y by 2 delta, and here also, okay, here also 3y by 2 delta only, not 3. Okay, 2 delta only. So 9y square by 4 delta square. Okay, and plus we'll get again 3y to the power 4. Again, this is 4 delta to the power 4. Okay, one term completed. Next, one more term is there, that is this one. So that will come here. So here we'll get minus yq by 2 delta q. This one into this. The minus of minus, and this is will be plus. So plus 3y to the power 4. 3y to the power 4, and this is 4 delta to the power 4. And next it is minus into plus, that is minus y to yq, that is y to the power 6, and divided by, and here we'll get 4 delta to the power 6 bracket close dy, again square bracket close. And now we need to do one thing, we need to integrate these equations with respect to dy. So if you integrate this equation, then this derivative term, let write it outside, then square bracket start, integration part is now implemented here. Then what will get, 3y by 2 delta dy, integration of this. So now integration of y dy, that means y square by 2. So y square by 2 means that we can write, this is 3y square. So this one I'll write 3y square by 4 delta. Similarly minus, again here y square by 2. So this will be like 9 by, here 9 by, what will get here, y to the power q, yq by 3. So 3 into 12, 4, that is 12 delta square, and here yq. Similarly plus same y to the power 5 will be there, so 3y to the power 5 and divided by 20 delta 4, minus, similarly here also this one we can write y to the power 4 by 8 delta to the power q. Okay, and yeah, next is similarly 3y to the power 5 by 20 delta to the power 4. Okay, and now this is, next one is the last one, that is y to the power 7, and here 6 into 4, that is 20, sorry, 7 into 4, that is 28 delta to the power 28, that is delta to the power 6 as usual. And now whole completed, and here we can give the upper limit, lower limit, that is 0 to delta. Okay, now again we need to put the value of delta here. So after putting the value of delta here, del by del x, square bracket start. Now here put the value of delta in place of y. So after putting the value of upper limit and lower limit is 0, so no need to put that thing, only upper limit is enough. So you can write this is 3 delta square by 4 delta minus 9 delta q by 12 delta square, minus here also same like delta to the power 5 20 delta to the power 4 minus here delta to the power 4 by 8 delta to the power 3 plus 3 delta to the power 5 divided by 20 delta to the power 4 minus again delta to the power 7 divided by 28 delta to the power 6 bracket close. Now upper limit, lower limit completed. Now again we need to just solve it, just we need to cancel all these values. Okay, so after cancelling you can see here what are the things we'll get here, that all value will be cancelled here, like delta square and 4 delta is there, so that means only 3 by 4 delta will be there. So after cancelling all this value we'll get like 3 by 4 delta, 3 by 4 here. If you see, this will be cancelled, Similarly, delta square is there, this will be cancelled. This is cancelled, and here also this total delta 4 will be cancelled. This is cancelled. Here also similar thing, only delta will be there. Same thing. See, this is cancelled. Now everywhere we will getting only delta in the top and denominator is there. So now if you see 3 by 4 delta, 3 by 4 delta. Now see, this is 3 by 4 delta. Another delta is where this is 9 by 12 delta. So we need to check it how many terms are there here, and so finally what we can do here, delta part we can take common otherwise. Okay, remaining part we can do it inside, or I'll write an equation like delta by del x bracket start. This is 20 is there, this one 20, this is 20. Okay, so 6 by, anyway I'll write here. So what I'll get, 3 by 4 delta, 3 by 4 delta, 3 by, see here also 3 by 4 will come. If I cancel this one, this will come 3 by 4, and this is 3 by 20. So 3 by 4, 3 by 4 delta, we got 1, 3 by 20, and this is 1 by 8, this is 1 by 8, this is 3 by 20, and this is 1 by 28. So all this value what is there, will keep 20 part one side, like what are the denominator 20 is there, that will keep 20. So similarly we can write this 6 by 20 delta, and this is minus 1 by 8 delta, and this is minus 1 by 28 delta, and this is bracket close. And if you do the LCM of this, like we need to solve this one, means we can get it delta by del x bracket start, and here you take the common of delta here, del of delta with respect to 6 by 20. This all this if you do it, then in the denominator we will get like 20 into, here 28 is there, 8 and 20. If you do the LCM of this, so you can get the solution of like 280 will be there, and here we will get 280, how much, 14 into 6, that is 84. And similarly this is 8 into 35, so numerator 35 minus 10. So finally if you solve this one, we'll get 39 by 280 of delta by del x. Okay, so now this one we got in terms of this value. Okay, now again what I'll do here, I'll just put a line here, and here again I'll write the equation what was there, tau naught. So tau naught by rho u square was there, so rho u square I'll take it to the other side, rho u square, again this is 39 del of delta by delta x, del x. So this one again we can write, this is in terms of this now, and 39 by 280 is there. So what I'll do again here, 39 by 280, and this is rho u square and del delta by del x. This one you can give an equation. Suppose let's give you an equation. Previously we have not given any equation, let's give it equation 1. Now we know that the shear stress in the Newton's law of viscosity, that shear stress tau naught also is given by, the tau naught is given by mu into du by dy. Now this one actually we need to consider at the surface level. At the surface level the distance will be 0. If you see this plate, a flat plate is there, so at this level the surface plate, your y equal to 0, that means the distance y thickness is 0 here. Now slowly if you take this one like this, the boundary, then we will get a velocity distribution here, and that is called du by dy. This one already we discussed number of times in the previous video lecture, you can see that one. So this equation tau naught equal to this one at y equal to 0, at y equal to 0. Now here what is the value of u? U is already given in this question, this one. Okay, so here the u equal to, we can write capital U, and this is multiplication of 3y by 2 delta minus y cube by 2 delta cube. This is the equation for the u. Now again you just put the value of here in this equation, like you derivative of this u, that means du by dy, because we need to identify this value du by dy. So du by dy equal to how much? Just to make a derivative of this, that means that you keep it outside, and this one, if you derivative of this one, will get like 3 by 2 delta, 3 by 2 delta minus 3y square. Derivative of y cube by this will be there. This will be 6 delta cube, 6 delta cube, and this will be bracket close. Now, hence we know that this du by dy at y equal to 0. Just put the value of y equal to 0. Now put y equal to 0, because at this condition what we have taken here, then what will get here? We'll get the value du by dy equal to 3 capital U by 2 delta, because this part is going to be total 0. Okay, now put this value in this equation. So what will get here again? Tau naught equal to, will get mu into 3 capital U by 2 delta, or you can write this 3 by 2 mu capital U by delta, and this one we can give another equation 2. Okay, now equating this two value of this shear stress tau naught, now we can write again, just equate these two equation, equating, okay, equation 1 and 2. So what we can write here? We got the equation of 39 by 280, and this is rho u square del delta by del x equal to 3 by 2 mu u by delta. Okay, now we can write this del delta, keep it one side, and remaining terms take it to other side. So what I'll write here, this is okay, delta part also keep it here, delta into del delta. Okay, and this one we can write. So what I have done here, just have, see this delta part and this part, this one I have taken to this side, this term, and this one I have taken to this side, and other terms are there as usual. So this is 3 by 2. So 3 by 2 already is there, mu into u into, this will be reverse, 280 by 39, and this is 1 by rho u square del x. Okay, now this one, if you multiply this, you'll get a value of, like, you can cancel some terms, like 2, this one can be cancelled, this is 140. Okay, and now if you multiply 140 into 3, so we'll get a value of 420. So 420 divided by, this is 39, and as usual remaining value is there, mu by rho u square, this is del x. Okay, so after that I hope you understand. Now what we'll do is this equation, let integrate this. After integrating, we'll get the value of, see, this is the del of del delta is there, and this side delta x is there. So let integrate this equation. So after integrating, write down, after integrating, we'll get the value, what we'll get here, this is delta square by 2. Okay, integration of this delta square by 2, and this is constant term is there, 420 by, this is 39, that will be taken outside, and this is mu by rho u. Now this will be there, rho u square is there. So here, yeah, rho u square, here u actually will be cancelled, so here will be only u, not u square, because after cancelling this u is there, and this u square one will be cancelled, so rho u is there, and delta x integration, this is x plus constant term c. Okay, now just to remember this term, so we'll go to the next one. So here, what is the term is there? Now here we can see x value is 0, okay, and delta value is 0. That means at the starting point, at the starting of the plate, we can see the x is 0 and delta is 0. Now if these two values are 0, then what is the value of c will get? C also will get 0. Okay, now again we can write here delta square by 2 equal to 420. The same equation we can write in this way. This is after putting the value of c equal to 0, we'll get this value, rho u into x. Now again we can write this value in terms of delta. What will get? Delta equal to root over of this is 420 into 2 is there, this side I have taken to this side, and this is divided by 39, and here we can write multiply of rho by u and into x. So now we need to solve this one, and you can find out the value of delta here, because that is our ultimate goal, to find out the boundary layer thickness. So here just I've solved this one, I'll get the value. So 420 by 420 into 2, that is 840. So what I'll do, 840 divided by 39 and root over of this 4.64. So you can write this is this value, we got 4.64, and this is root over of mu into x by rho u. Now we got this value, this is final, but what is given in the question, we need to find out this boundary layer thickness in terms of Reynolds number. Okay, Reynolds number equal to what? We know that Reynolds number equal to R equal to rho v, rho u, rho v L by mu. So here rho u is there, that means rho v is there, and here denominator mu is there, but one more x required or length required. So what I'll do, I'll x multiply and x I'll divide here. So here x, that is the length, so rho vx or rho ux by mu. So this part you can write as a Reynolds number. So again I'll write this is delta equal to 4.64, and this is root over of this one, you can get x square by re x. Okay, now similar thing we can just again just solve it, this one x by root over of re x, and this is equation number 3. So this one, the value of delta boundary layer thickness in terms of what? In terms of Reynolds number. Similarly, what we need to find out the next one is the shear stress, suppose. So shear stress value tau naught. So tau naught equal to, we know that tau naught equal to what? We got the equation actually, that is previously what we have got this equation. Here if you see that delta value is there and x value in terms of RA number is there, that is delta. So we know that we can write this is tau naught equal to 3 by 2, and this is mu into capital U divided by 4.64x and divided by root over of Rex. Okay, now this is the term, I can put it here. Now here if you see this value, where I have written this one, yeah, this one you can see. Now see, this is the values there. Okay, now what I have done, 3 by 2 mu by delta, this one 3y by 2 delta, 3y by 2 delta, whatever the equation was there, just I put the value there. So here we can get again we can get this 3 by 2 into 4.64, that is 4 into 2 8, and this is 9 point something will get here. So I'll write this value, that is 3 by 9.64 into 2, that is 128, that means 9.28, and this is mu u, and this is root over of Rex and divided by x, and finally again we need to find out this value, so that we can write this is tau naught equal to 3 divided by 9.28. So this one we need to do 3 divided by 9.28, so that is nothing but 0.323. So we'll get the value tau naught equal to 0.323 mu u by x root over of Rex. Okay, so shear stress also we got the value in terms of Reynolds number. Okay, now so third one is, it is given the coefficient of drag, or sorry, one drag force is there, drag force need to be calculated. So drag force equal to that, we need to take the equation from the von Karman equation, that is integration 0 to L, and this is tau naught and then V into dx. See, all are related to each other. Once you get this value, we can put this value here. Similarly, again next value is this one, so you can put the value here. Tau naught we got, now we need to put the value of tau naught. So integration of 0 to L, and this is 0.323, and this one mu into u by x root over of rex into b into dx. So this is the value of what, the tau naught. So now we need to find out, we can integrate this equation and we can find out the value of fd here. Okay, now this integration, it will take some time. That means here 0 to L is there. Now what I'll do, constant term will take it to outside, that is 0.323 integration 0 to L and mu into u by x, and this one we can write, this is rex, we can write this is rho ux by mu, okay, into b into dx. Again this one we can write, okay, let's write here. So let's divide in this way, and here we can write, this one I will write here 0.323 and mu into u, and this is root over of rho u by mu, and this is b into, let's separate this one because these are a constant term, let's take it to outside. So integration part only 1 by root over of x is there. So here we'll get x to the power 1 by 2, so that integration only need to done. So now after integrating we'll get 0.323, and this is mu u root over of rho u by mu, and this is, see, this one I can write like x to the power 1 by 2, and here dx is there. Now we take to the denominator side, it will be minus, then next part we can write this is minus 1 by 2 into dx. Okay, then after integrating this one 0 to L, if you write, then we'll get 1 by 2. What we will get here, this is 1 by 2 and here 1 by 2, and we will get minus 1 by 2 was there, so 1 minus 1 by 2, that will be there, and 0 to L. So once you solve this one, we'll find out final equation I'm writing here, that is 0.2323 to here. Now we need to write here actually 2 into this one is there into b into root over of L. Okay, so this will be there, and finally you can write this one 2 into this one, you can multiply, so that will be 0.646 mu into u and root over of, now this one rho ul by mu into p. This one again you can give an equation 4. Okay, now we need to find out that this is fd, this is the value of fd. Now the next term is we need to find out the value of coefficient of drag. The coefficient of drag is, again we need to go back to the equation what we have derived. This is fd. In the last lecture I have told you how to find out the coefficient of drag, that is fd by 1 by 2 rho a u square. So now see, again fd is going to implement here. So fd equal to, again write down this value 0.646, and this is mu into u root over of this rho ul by mu, this is nothing but Reynolds number, into b, and divided by this is 1 by 2 area you need to write here length into width, and this is u square. Now if you see, you can just cancel all this value, cd equal to, so what will get here 0.646 mu into u, and this is root over of what is there, that 2 part you can take it to the upper side, so you write down rho ul by mu, and this is 1 by 2, you'll take it to the other, like here you can write this is 2 into, okay, 1 by 2 I have taken to there. Now again some terms will be cancelled here, okay, this will be cancelled, okay, and bl is there, so that one, this is square root is there, mu to the power 1, here it is minus 1 by 2 is there. So okay, let me write here, this is b term is here, that is square root of, this is b is there, so b can be cancelled here. I have not cancelled that one right now, so in the denominator part what is there, let me write here, this is 1 by 2 I have taken already, so b into L. Now again without confusion, let's write directly here. So what I'll write, this is 2 into 0.646 into mu by rho ul, mu by rho ul into root over of this. As usual it is there, we can write this is okay. And finally what will get 2 into this one, so I can write 2 into this one, that will be 1.24692, that is 292 and divided by this value will come. So this is root over of, now see this one and into this one, if you solve this two part, this square root is there, only this single term, so you can write this is will get rho ul by mu. Now finally this one is nothing but we can write CD equal to 1.292 divided by root over of Reynolds number. This is Reynolds number, we know that, so we can write this is the Reynolds number. On behalf of length it is given, so I'm writing L. Okay, so this is the final equation, and you can give an equation. This is 5. Okay, so now we can see what the question is given. Based on the question, we have identified everything: coefficient of drag, shear stress, boundary layer thickness. So everything is calculated based on this velocity profile. Okay, so I hope you understand this derivation, though it is a little bit lengthy, but if you do sequentially one by one step, you can easily do it. And the thing is that we need to remember some equations like this one, the one common equation what we have derived in the previously, this one equation. Then next is this formula, tau naught. Okay, tau naught already we got from there, and this one, that drag force, this one we have taken from the one common equation. Similarly, the coefficient of drag, these two equations we need to remember. Okay, because all things we have seen that all are interlinked with each other, so once one first part of it is wrong means everything will be wrong. So while you do the solution, be careful, and still if you are having doubt in this equation, you can give a comment in the comment box. I'll try to solve it. Thank you.